We're going to continue talking about acceleration in special relativity by talking about Bell's spaceship paradox. Bell's spaceship paradox will lead us to inventing Rindler coordinates, our first set of curvilinear coordinates in this relativity series. Bell's spaceship paradox is one of many so-called paradoxes in special relativity, like the twin paradox and the ladder paradox. At first, these paradoxes seem like contradictions that indicate flaws in special relativity, but more careful thinking reveals that there is no paradox at all and special relativity works just fine. Bell's spaceship paradox works like this. Let's say that there are two spaceships some distance d apart. There is a string that ties the two spaceships together. The string is exactly long enough to cover the distance between the spaceships. If the spaceships move even slightly further apart, the string will break. Einstein is standing stationary halfway between the two spaceships, and sends a light signal to each one, which tells each ship to begin accelerating to the right. The spaceships will both accelerate in the same manner, so that they are always traveling at the same velocity according to Einstein, and the distance d between the ships never changes according to Einstein. The question is, does the string between the ships break? Some people might argue that the string will not break, because the distance between the two ships does not change according to Einstein. Others will argue that the string does break because once the string starts moving, it will undergo length contraction, and that it will become too short to cover the distance d between the ships and snap. So which argument is correct? Does the string break or not? Let's first examine this problem with accelerating spaceships in Newtonian physics. You should already know that in Newtonian mechanics, an object traveling with constant acceleration travels in a parabola curve, which looks like this on a space-time diagram. Now let's look at a pair of spaceships that are stationary some distance d apart. If the spaceships start accelerating to the right with the same acceleration, then their world lines in space-time would look like this. The parabolic world line of the blue spaceship in front is an exact copy of the parabolic world line of the orange spaceship in the back, just shifted to the right in the spacetime diagram. A stationary observer would see the distance d between the spaceships remain the same throughout their journey. And since this is Newtonian physics, time and space are absolute quantities that everyone agrees on. This means that all observers agree the distance between the spaceships stays the same. Now let's consider accelerating spaceships in special relativity. Remember from the previous video, an object traveling with constant proper acceleration in special relativity travels on a hyperbolic curve, which approaches the speed of light but never reaches it. Let's again look at a pair of stationary spaceships that are some distance d apart. If both spaceships start traveling to the right with the same proper acceleration, then their world lines are hyperbolas that are exact copies of each other, with the front ship's world line shifted to the right compared to the back ship's world line. Once again, a stationary observer would see the distance d between the spaceships remain the same throughout their journey. However, this is now special relativity, and distances are now relative. Recall in the last video that we said a curved world line measures time and space using a different spacetime basis at every point along the curve, where the time basis is tangent to the curve and the spatial basis vectors are orthogonal to it. According to these instantaneous reference frames of the rear spaceship, the distance between the ships becomes greater than d. The ships are moving farther and farther apart from each other, according to the rear spaceship. Now let's change things slightly. Let's say that we want the spaceships to remain the same distance d apart in their own reference frame, even as they are accelerating. So the blue spaceship in front must always be a distance d in front of the orange spaceship in the back. Then the front ship's new world line would look like this. It is no longer an exact copy of the rear spaceship's world line. In fact, it is less curved. This means that in order to maintain a constant distance d between the ships in their own reference frames, the orange ship at the back must accelerate harder than the blue ship in front. Because of this, a stationary observer will see the orange ship at the back catching up with the blue ship in the front, with the distance between the ships getting smaller and smaller, even though the two ships see themselves at a constant distance apart in their own reference frames. So in the first scenario, where the stationary observer sees a constant distance between the ships with equal proper acceleration, the observers on the ships see themselves moving apart, and so a string between them that's moving along with the ships would break. But in the second scenario, where the ship at the back accelerates harder to maintain a constant proper distance between the ships, the string doesn't snap because the distance between the ships doesn't change. The stationary observer sees the distance between the ships get smaller and smaller. This is the resolution to Bell's spaceship paradox. The string will break if the ships accelerate with the same proper acceleration. But if the ship in the back accelerates harder in just the right way, the distance between the ships stays the same in their own reference frames, so the string doesn't break. We can use the idea of maintaining the same distance between accelerating spaceships in their own reference frame to create a curvilinear coordinate system called Rindler Coordinates. Rindler Coordinates show us how time and space are viewed from the perspective of an observer that is traveling with constant proper acceleration. This means that Rindler Coordinates are a spacetime coordinate system for a non-inertial frame of reference. To create the coordinate system, an observer on an accelerating spaceship needs to know how to measure distances in front of and behind them. Instead of looking at two accelerating spaceships, let's look at a whole train of accelerating spaceships. Each ship will maintain a constant distance d from each ship in front of and behind it. In the previous video, we derived the equations for the hyperbolic world line of the first of these spaceships, where the time ct is given by a hyperbolic sine, and position x is given by a hyperbolic cosine. The hyperbolic angle is given by the proper acceleration, alpha, divided by the speed of light c times the proper time tau. For reasons that will come up later, I'm going to rewrite this hyperbolic angle as alpha over c squared times c times tau. This spaceship accelerates with proper acceleration alpha and maintains a constant distance c squared over alpha from the origin behind it, which is also the Rindler horizon. We know that this distance is constant because when we calculate the spacetime interval, s squared, which is ct squared minus x squared, and then take the square root of its negative value, we get a constant proper length c squared over alpha. I may sometimes write the equations of motion for an accelerated observer using d instead of c squared over alpha. D is the distance between the first spaceship and the Rindler horizon at the origin, and it's a convenient unit of distance to use when talking about distance in Rindler coordinates. I don't know if this distance d has an official name, so I'm just going to call it the Rindler distance. And we know that the proper acceleration is alpha because we can calculate the foreacceleration vector a by taking two time derivatives with respect to tau, and then taking the negative square root of a dot a, and we get alpha. So given that the distance between the rocket and the Rindler horizon is capital D, let's say that we want another accelerating rocket that maintains the same constant distance d from the first rocket. In other words, the second rocket must undergo proper acceleration and maintain a distance 2d from the Rindler horizon. We can do this by taking the equations of motion for the first rocket and dividing the proper acceleration alpha by 2. This means that the proper distance from the origin is now twice as big, 2 times c squared over alpha, or 2d, as desired. The four-velocity dotted with itself, u dot u, is c squared, as required. And the proper acceleration, the square root of negative a dot a, is now half as big, alpha over 2. So as we said before, in order for two accelerating spaceships to maintain a constant proper distance from each other, the spaceship in the back must accelerate harder, alpha in this case, and the spaceship in front does not accelerate as hard, alpha over 2 in this case. We can continue this pattern to get spaceships traveling with proper acceleration alpha over 3, alpha over 4, alpha over 5, and so on. All of these spaceships maintain a constant proper distance d from each other, but each spaceship must accelerate harder than the spaceships in front of it. When we have a collection of particles that accelerate together in such a way that the proper distances between them do not change, we call this Born rigid motion, after the physicist Max Born. And again, note that all of these spaceships have a common Rindler horizon located at the origin. We can take this collection of world lines for accelerating spaceships and use them to build a curvilinear coordinate system for spacetime. Taking the equations for constant proper acceleration, let's replace the coefficient in front, c squared over alpha, with a continuous variable x tilde. The x tilde variable lets us continuously choose a hyperbola with any constant proper distance from the origin of our choice, with this constant proper distance from the origin just being x tilde. We can also replace the expression c times proper time tau with a new time coordinate ct tilde. This time acts as a hyperbolic angle for the coordinate system and lets us pick a particular instant in time for all of the spaceships. These new coordinates, ct tilde and x tilde, form a curvilinear coordinate system that indicates how time and space are observed from the point of view of an accelerated observer with constant proper acceleration alpha, and whose Rindler horizon is at the origin. Unlike the standard spacetime coordinates, the Rindler coordinate system only covers a portion of our spacetime diagram, since accelerated observers cannot see anything beyond their Rindler horizon. The Rindler horizon line represents a line where the hyperbolic angle ct tilde approaches positive infinity. This lower diagonal line does not represent a horizon because light can cross through it, but it still represents a boundary of the coordinate system, where ct tilde approaches negative infinity. So now we have equations that change between the standard spacetime coordinates ct and x and the new Rindler coordinates ct tilde and x tilde. In some ways, this is similar to the Lorentz transformations we've seen before, which also convert between two sets of spacetime coordinates. The difference is, this time, the new Rindler coordinates are curvilinear coordinates, and the transformation cannot be represented by a matrix multiplication. In this next part of the video, I'm going to state various properties of the Rindler coordinates that will help us understand how accelerated observers view spacetime. In particular, I'm going to show that all clocks on the different accelerating spaceships will tick at different rates. In other words, each spaceship measures a different proper time from the others. I'll also calculate the proper acceleration for each spaceship. And finally, I will show that the formula for the spacetime interval s squared from the origin does not depend on time. At the end of this video, I'll talk about how the speed of light can have values other than c in Rindler coordinates. The curves of constant x tilde are the curves of constant position according to an accelerated observer. These curves are a series of hyperbolic curves that all have the same Rindler horizon at the origin. Hyperbolas that are separated by equal proper distances at one point in time will maintain that same proper distance from each other for all time, just like the spaceships we saw before. The time coordinate ct tilde increases moving upward. The curves of constant ct tilde are actually straight lines that radiate from the origin. These are the lines of constant time. These show us where all the spaceships are located at any given moment along their journey. It's important to note that the t tilde coordinate is not the proper time tau. This means that t tilde is not the time measured by a clock on the spaceship traveling along a given hyperbola. The proper time tau measured by a particle on a hyperbola of constant x tilde is actually given by tau equals alpha over c squared times x tilde times t tilde. Or equivalently, tau equals x tilde over the Rindler distance d times t tilde. I'll give a formal proof of this fact in Relativity 105 Part D, when I discuss proper time along curves, but here is some quick informal reasoning for it. Recall that given the equations of motion for the first accelerating spaceship with distance d from the origin, we got the equations of motion for the ship located at 2d by replacing alpha with alpha over 2 in the equations. If we rewrite c squared over alpha as d, this is the same thing as replacing d with 2d. If we compare the equations of the second ship to our general Rindler hyperbolas, we can see that ct tilde over d corresponds to c times proper time tau over 2d. Canceling the c's and the d's, we get that 2 times t tilde equals proper time tau. But we can also see that x tilde corresponds with 2d. So this factor of 2 is really the ratio between x tilde and d. Subbing this in, we get that the proper time tau for any spaceship of any position is x tilde over d times t tilde. So given this formula for proper time along curves of constant x tilde, this means that clocks located at larger x tilde values will tick more quickly. If we look at our 5 accelerating spaceships, on a line of simultaneity t tilde equals 1 second, we find that each spaceship has counted a different proper time on its clock. Even though all of these events happen at a simultaneous time for all the ships, we find the ships at larger x tilde values have measured longer proper times on their clocks. It's important to remember that the t tilde coordinate is equal to the proper time only for the first spaceship at x tilde equals d, and nowhere else. All the other spaceships will measure different proper times according to this equation. Also, the proper acceleration alpha is a parameter for the Rindler coordinates. There are actually several different versions of Rindler coordinates, each with a different value for the alpha parameter. Particles on a world line of constant x tilde will have a proper acceleration of c squared over x tilde, which is also equal to alpha times d over x tilde. To prove this, recall on world lines of constant x tilde, that proper time tau equals x tilde over d times t tilde. We can use this to prove that d tau by dt tilde is x tilde over d, since x tilde is constant. And taking the reciprocal of both sides, we get that dt tilde by d tau is d over x tilde. If we start with the CT formula for Rindler coordinates and take the derivative with respect to proper time, we turn the sinh into a cosh and get a c over d term outside. We also get a dt tilde by d tau chain rule term. We don't take the derivative with respect to x tilde because we assume x tilde is a constant. Another derivative turns cosh back into sinh, and we get another c over d and another chain rule derivative term. Subbing in d over x tilde for the chain rule term, we can see that the d's cancel out, and we can also cancel one x tilde, and we end up with c squared over x tilde out in front. We can calculate the second derivative of x in a similar way. And calculating the proper acceleration, the square root of negative a dot a, we get c squared over x tilde, which is also alpha times d over x tilde. This formula basically means that the proper acceleration of each spaceship decreases as x tilde increases, which matches what we've seen. We showed in Relativity 104 Part E that the Lorentz transformation does not change the form of the formula for the spacetime interval s squared. All inertial frames calculate s squared by taking the time coordinate squared minus the space coordinates squared. But if we substitute in the Rindler coordinates for ct and x into the formula for s squared, we see that the formula for s squared in the Rindler coordinates has a different form that doesn't involve the time coordinate at all. This is because the Rindler coordinates are not obtained with a Lorentz transformation, and Rindler coordinates represent a non-inertial frame. So the formula for the spacetime interval looks different than what we're used to for inertial frames. Since the spacetime interval s squared doesn't depend on the time coordinate ct tilde, this means that the spacetime interval doesn't change with time for any of the spaceships traveling along the hyperbolas. And since the spacetime interval is always a negative number, negative x tilde squared, this confirms that x tilde is the proper distance from the origin at any point in the Rindler coordinate system. Each hyperbola is a curve of constant x tilde, and so it has a constant proper distance from the origin, or the Rindler horizon. As I stated before, the Rindler coordinates are only valid for a portion of the spacetime diagram. They only work for positive x, and when ct is between negative x and positive x in the standard coordinates. Now, these equations are a bit inconvenient because they are mostly useful for changing from Rindler coordinates ct tilde and x tilde to the standard coordinates ct and x. It's possible to invert these formulas to come up with new equations that change from the standard coordinates ct and x to Rindler coordinates ct tilde and x tilde. We've already seen that the spacetime interval, which is ct squared minus x squared in the standard coordinates, is minus x tilde squared in Rindler coordinates. If we multiply both sides of the equation by -1 and take the square root, we get a convenient formula for x tilde in terms of ct and x. We take the positive value of the square root since the Rindler coordinates work in the positive x tilde direction. Also, if we divide the formula for ct by the formula for x, we see that the x tildes cancel, and sin h divided by cos h is just the definition of hyperbolic tangent, tanh. We can eliminate tanh by using its inverse function, arctanh, on both sides, and then multiply both sides by c squared over alpha to solve for ct tilde. We now have formulas that convert from the standard coordinates to Rindler coordinates and back again. To summarize this video, we learned about Bell's spaceship paradox. If a set of spaceships accelerate together with the same proper acceleration, then the distance between the spaceships is constant when viewed from a rest frame. However, in the frames of the spaceships themselves, the spaceships will appear to be moving apart. Conversely, if the spaceships accelerate in such a way that the proper distance between them remains constant in their own frames, then each ship will have a different proper acceleration. The ship in the back will have to accelerate harder in order to keep up with the ship in the front. In this case, the stationary observer observes the spaceships moving closer and closer together. Both spaceships will have a common Rindler horizon behind them. In order to look at space and time from the perspective of someone undergoing constant proper acceleration, we derived the Rindler Coordinates, which are curvilinear coordinates for spacetime. A traveler on a constant x tilde coordinate will have a constant proper acceleration of c squared over x tilde. The proper time for a traveler with constant x tilde coordinate is alpha over c squared times x tilde times t tilde. We also saw that the formula for the spacetime interval, s squared, was just negative x tilde squared, which is different than the formula that we're used to seeing in inertial frames. We also derived formulas to convert between the standard coordinates and the Rindler coordinates in both directions. The last thing I want to mention is that in Rindler coordinates, it's possible that the speed of light can be less than c or greater than c, where c is the speed of light in an inertial reference frame. However, it's important to note that the truth of this statement comes down to the definition of speed as dx tilde by dt tilde, which is not an invariant based on 4 vectors, and so different observers will disagree on it. The reason that this definition leads to the speed of light not being c is because t tilde is not equal to the proper time tau in Rindler coordinates, except in the special case of an observer that is located at the Rindler distance d. This observer will always measure the speed of light to be c when measuring light beams locally right next to them. The calculation of the speed of light to be not equal to c occurs for non-local regions of spacetime far from this observer, where the t tilde coordinate does not equal the proper time tau. In the future, with non-inertial coordinate systems and in general relativity, we will need to be very careful when interpreting spacetime coordinates, because unlike with inertial frames, the spacetime coordinates will not always have obvious physical meaning. So given the spaceships in the Rindler coordinates, let's find the speed of light in the Rindler coordinates dx tilde by dt tilde at various positions along the horizontal axis. The equations of these light beams in the inertial coordinates are x equals ct plus x naught, where x naught determines the initial position of the light beam along the x-axis. I'm going to go through this derivation quickly, so pause the video if you want to look at it more carefully. We know that the Rindler x tilde coordinate squared equals x squared minus ct squared in inertial coordinates. We can sub in the equation of our light beam, ct plus x naught, for the x variable. We can expand the square, cancel ct squared, and bring all the terms to one side, and replace ct with x tilde times sinh of ct tilde over the Rindler distance d. Since this is just a quadratic in terms of x tilde, we can use the quadratic formula to solve for x tilde. This 1/2 cancels with this 2, and the 2 squared and 4 under the square root sign. We can also factor out x naught to the front of the expression. The fundamental hyperbolic trig identity tells us that 1 plus sinh squared equals cosh squared, and we're going to enforce that x tilde is positive to get the positive square root sign. It can also be shown that sinh plus cosh equals the exponential of the hyperbolic angle. So we have a formula for x tilde, and if we take the derivative with respect to t tilde, we get c over d times x naught times this exponential. If we restrict this formula to the horizontal axis, where ct tilde equals 0, then we get the speed of light is c over d times the initial position x naught. This means that a beam of light sent from the Rindler distance d has a speed c. A beam of light sent from the position 2d has a speed 2c. A light beam sent from 3d has speed 3c, and a light beam sent from 4d has speed 4c. Also, a light beam sent from 1/2 d has speed 1/2 c. And a light beam sent from the Rindler horizon at the origin has 0 speed, as we discussed in the last video. So on the horizontal axis, at the Rindler distance d, the speed of light in Rindler coordinates, dx tilde by dt tilde, is equal to c. As we can see, this light beam travels one grid unit of distance in one grid unit of time, in this grid box. For distances less than the Rindler distance d, the speed of light is less than c. A beam of light travels less than one grid unit of distance in one grid unit of time. And for distances greater than d, the speed of light is greater than c. A beam of light travels more than one grid unit of distance in one grid unit of time. So this idea that the speed of light might not be equal to c can seem pretty confusing. So how do we interpret this? Remember, the second postulate of special relativity says that the speed of light in a vacuum, c, is the same in all inertial frames. This means that in an inertial frame right beside a light beam, the frame will always measure light as having a speed of c. So whether we're in a global inertial frame or an instantaneous inertial frame at one instant along a curved world line, we'll measure the speed of light right beside us to have speed c. And what we're really saying here is that the derivative of proper length with respect to proper time at a given point is always c for a light beam's world line, where the proper length and the proper time are measured according to inertial frames. However, it's very important to realize that the clocks in non-inertial frames can tick at different rates. This means that non-local beams of light can have a speed different from c, because its speed is being measured with a non-local clock. Mathematically, this means that the derivative of proper length with respect to proper time for a light beam is not necessarily equal to the derivative of the space coordinate with respect to the time coordinate for a non-inertial coordinate system. Let's visualize this with space-time diagrams. In inertial coordinates, we know that along lines of constant position, the proper time tau is just equal to the coordinate time t. So if we place clocks tau 1, tau 2, and tau 3 at various positions and set them all equal to 0, then at this line of simultaneity a bit later, the clocks all read the same value of 1. So in inertial coordinates, the coordinate time t is equal to the proper time tau if we remain at a constant position, and this is the same time measured for all positions x. However, in Rindler coordinates, we know that along curves of constant x tilde, the proper time along each curve depends on the position x tilde. So if we start clocks tau 1, tau 2, and tau 3 at 0 at various positions, then at this next line of simultaneity, they will all read different times, because more proper time passes at larger x tilde positions. Clocks in Rindler coordinates will tick at different rates depending on their position, and so the coordinate time t tilde is not always equal to the proper time tau for a given location. It's also worth mentioning that in global inertial frames, the position coordinate is equal to the proper length along lines of constant time. And this is also true in the Rindler coordinates as well. The important thing to note is that the coordinate time t tilde is not equal to the proper time in Rindler coordinates. If we return to our 5 spaceships, along the line of simultaneity at t tilde equals 1, the first spaceship at position d counts a proper time of 1 on their clock. But according to our formula, the fourth spaceship at position 4d counts 4 units of proper time on their clock. A beam of light next to the first spaceship will have a speed in Rindler coordinates of dx tilde by dt tilde, which is just dl0 by d tau 1, which is the ship's local proper time. As stated before, the local speed of light in an instantaneous inertial frame is always c. If we measure the local speed of light at the fourth spaceship using the local proper time tau 4, we also get a speed of c, because this is also an instantaneous inertial frame. However, if we measure this light beam at the fourth spaceship using the Rindler coordinates dx tilde by dt tilde, we're not measuring this light beam using a local clock, since 1 unit of t tilde time is only equal to a quarter of the local proper time tau 4 on the fourth rocket. The result is that we get the speed of the light beam to be 4c, because it was measured with a non-local clock. So the important points to remember for non-inertial frames are that the spacetime coordinates don't always have obvious physical meaning. It's possible that the coordinate time is not always equal to proper time along lines of constant position, and it's possible that the coordinate position is not always equal to proper length along lines of constant time. Therefore, the local speed of light beams is not always equal to the coordinate speeds of light beams measured non-locally. Now, all of this might seem pretty confusing. To understand this better, we're going to study the Jacobian Matrix and the Rindler metric for getting proper time along curves in the next couple videos. In this video, we're going
Download the code here. I also want to look at how to use Jupyter Notebook on VS Code. Because I think it's better to learn from the videos I watched. It's gonna be better to learn the many libraries in Jupyter. But I don't want to open on the browser. And I saw this guy doing coding on Visual Studio Code with Jupyter Notebook. I wish this guy had a playlist on quantum mechanics as well. These videos are really good.
All right, welcome to.
This playlist should be helpful to understand neural networks, I guess, since everything is matrix multiplication and vector manipulation from the stuff I've seen so far. I'm curious to see what parts of quantum mechanics involve complex plane calculations. And how they tie in probability in quantum mechanics.
Hi guys, I'm Jade. Lovely to meet you. So the Schrodinger equation is one of those things that pops up a lot in like quantum science articles and journals and stuff, but the journalist doesn't usually go into what it means, which is fair because it's a fairly complex topic. So today I just wanted to share with you guys like what it actually means, so next time you read it in an article, you can get a better gist of what it's about. So the short version is, the Schrodinger equation tells us everything we can possibly know about a quantum system. It's basically the F equal ma of the quantum world.
If you throw a ball and solve F equal ma, you can predict its position and momentum for any moment in time. Once you have these two, you can derive basically everything else you could possibly know about it. Velocity, energy, etc. But when we get down to particle land, Newton's equations don't work anymore. If we put a particle in a box and we want to know where it is, F equal ma just doesn't cut it. The Heisenberg uncertainty principle says that we can't know both the exact position and momentum of quantum objects, but we can know other things, like the energy levels and the wave function, which we'll explore in this video. But that information is all inside the Schrodinger equation, and with some hardcore mathematics, we can tease it out.
Now, the long version. So before I get started, I should say that this is the time-independent version, meaning that it doesn't involve time. And if at any point throughout the video you get lost, don't worry. Even Schrodinger didn't know exactly what his equation meant.
So let's say we have a quantum system, an electron in a box. We want to know everything we can about this electron so we can make predictions. Where it might be, what energy level it might be at, these answers are all buried within the Schrodinger equation. So first, let's start with this guy, the pitchfork thing. This is the Greek letter psi, and it stands for what's called the wave function. It tells you where the electron is likely to be,
But not where it will be. See, quantum objects are sneaky in that you can't predict exactly where they'll be until you measure them. You can only predict where they'll probably be.
Say there's this kid you know. You've grown up with them your whole life. They're locked in their room with their homework, a PlayStation, and a bed. If you had to
A superposition of all possible places at the same time. You may have heard the famous thought experiment Schrodinger's cat.
who's in a superposition of being dead and alive until the box is opened and it's allowed to have. Now before I go into what that means, I just want to point out that the way this equation is arranged, these values are the ones we're trying to solve for. So it's telling us that, hey, if you do all this stuff, you can find out the energy levels of the wave functions of the electron. And if we know these two things, we can derive everything else we can possibly know about the particle, just like the position and momentum of a ball.
But let's backtrack a sec. What do I mean when I say energy levels the electron is allowed to have? Like it's a grown electron, it can have whatever energy levels it wants, right? Well, no. In the regular world we see around us, energy can go up and down in a smooth, continuous way. But this isn't the case in the quantum world, and the reason comes from the wave-like nature of the probability distributions.
Because our particle is inside the box, it has a zero probability of being found in or outside the wall. So this means the wave function always needs to be zero there. Otherwise, there's some probability that the electron could be outside the box, which we know it's not. That means that the electron can only have
I still don't understand really well how gravity is connected to the electromagnetic field.
certain frequencies associated with it. This frequency is allowed as the wave function is zero.
In the current understanding of things based on what people are saying today.
At both edges, and this frequency is not. This frequency is allowed, and this one is not. So Einstein discovered that energy is actually proportional to frequency by this relation, E equals hf, where E is the energy, F is the frequency, and this h here is Planck's constant. Don't worry too much about that h for now. All you need to know is that it's a constant, which means its value doesn't change. So if only certain frequencies are allowed inside the box, and this is a constant, then it follows that only certain energy levels are allowed inside the box too.
This property of discrete or quantized values is where quantum mechanics gets its name. Things that can take on continuous values in the regular world, like energy levels, can only take on certain quantized values at the quantum scale. Now let's look at the other side of the equation.
We know what we're solving for, the energy levels and the wave functions. But how is all of this going to help us get there? Well, overall energy is made up of kinetic energy and potential energy. If a skateboarder is on a skate ramp, they'll be traveling at some speed and have some kinetic energy. But when they stop at the top, they still have energy. It's just transformed into a different kind, potential energy. The entire energy of the system is just the kinetic energy plus the potential energy. And while it can move back and forth between those two states, its total value is always conserved. Sometimes, potential energy is written as a V. So this term is the potential energy of the wave function. So if this is the potential energy, that must mean that this term here is the kinetic energy. I know it doesn't really look like any kind of kinetic energy equation we've seen before, right? So here's the derivation if you don't believe me. So if we can solve for the potential and kinetic energy of our quantum system, this will tell us the energy levels allowed. And that's everything there is to know about our little electron. So what would some typical Schrodinger solutions look like? Well, to this particular problem, all the solutions to the wave functions take these two forms. And the energy equation that popped out was this.
Great, Jade, so what the hell does that mean?
Well, the first thing to note is that every term in this expression is either a constant or a whole number. H bar is a constant, 2 is obviously a constant, m, the mass of the electron, is a constant, pi is a constant, and L, the length of the box, is a constant, and n stands for the different states of the electron, and they're all whole numbers, 1, 2, 3, etc.
So then the energy E can only have certain values. It's quantized. But what about the wave function? Where is the electron?
Well, let's look at this guy when the electron is in its first energy state, when n is equal to 1. We get this. That's one of the wave functions of the electron, and if we square it, we get the probability distribution, aka where the electron is likely to be. We can see that there's a high probability that it'll be found in the middle here, but a 0 probability it'll be found right at the edges. Here are some more wave functions and probability densities for other energy states. See how the wave function is
Here's the thing that I'm confused about, is probability is always in relationship to space-time. So how can you know that the probability is going to be like that? don't understand how they make these conclusions about it. Because saying something about the energy state, and then the probability is gonna be a certain probability of the electron being or the particle being somewhere, but that depends on the observation of it, the space-time thing, and the relativity of the space-time. Because if we assume gravity and acceleration determines the relationship between observers and how time and space are different between them, then the probability has to follow the same rules. I have no idea.
Always 0 right at the edges. This took me an entire semester of a physics degree to understand, and what really helped me was working through a lot of problems and taking the time to build a strong intuition. Brilliant.org has an entire course dedicated to quantum mechanics, which starts with the experiments which first discovered quantum behavior and leads up to the derivation of the Schrodinger equation. It has examples you can work through at your own pace. I actually just went through it to refresh my memory and learned some things I didn't know and definitely understood some things better. They also have heaps of other courses, mainly on physics, math, and computer science, and they're always adding more. The first 200 people to click the link below and sign up will get a 20% discount. Just go to Brilliant in the description. It includes the derivation of the Schrodinger equation as well as the solutions and some other interesting stuff like random questions to my professor. So guys, please be honest, do you understand the Schrodinger equation a bit better?
I can't quite put into words yet what I'm trying to say about probability and space-time. It's just something doesn't make sense in my mind about it. I guess it's the notion of probability and what it means, because my mind probability is already assuming a correlation between space-time and geometry. I think that's the point. You can only make conclusions about probability after you have a sample size, and that sample size is the observation of the space-time. So how can you say that how can you make conclusions about it if the measurement itself depends on the stuff you're trying to make sense of? You're trying to use the measurement of space-time to determine the probability that the space-time is a certain way and follows certain rules, but it's kind of like a paradox. Because the only thing you can make conclusions about is the probability and not the thing itself. So how can you know if there is a direct correlation between probability and the geometry of space-time?
Consider a particle of mass m that is forced to move only in the x-axis by the force f of x of t. If classical mechanics give me the x as a function of t, I should be able to find its
I think
velocity.
I'm gonna make some coffee and watch this playlist. Keep watching the playlist before I move on to the other stuff. Yeah, I'll be right back.
going to talk about basis vectors and the Jacobian for curvilinear coordinates. These tools will help us deal with the mathematics of non-inertial frames in special relativity, and also eventually the curved spacetime of general relativity. Throughout this video series, I've been trying to emphasize that we should think of vectors as being made of both basis vectors and vector components. Also, when basis vectors change in one way, a vector's components will change in the opposite way. We saw this first in 2D space, where making the basis vectors twice as big with a matrix of 2's results in a vector's components becoming twice as small, with a matrix of 1/2. Then, in Galilean relativity, we saw that when the spacetime basis is transformed with a Galilean matrix, a vector's components are transformed with an inverse Galilean matrix. Then, in special relativity, when the spacetime basis is transformed using a Lorentz matrix, a vector's components are transformed using an inverse Lorentz matrix. In the last couple videos, we've learned that an accelerating object has a different spacetime basis at every point along its curved world line. In order to change basis between an inertial frame and a non-inertial frame, we need a transformation that knows how to change basis at every point along the accelerating object's world line. The matrix that helps us do this is called the Jacobian matrix. When basis vectors transform with a Jacobian matrix, a vector's components will transform using the inverse Jacobian matrix. To understand the Jacobian matrix, we need to understand two ideas. Number one, we need the multivariable chain rule, and number two, we need to think of basis vectors as tangent vectors along coordinate curves. If you understand these two ideas, you already know everything you need to know about the Jacobian matrix. Everything afterward is just filling in the details and giving examples. I've covered basis vectors and the Jacobian before in videos 2, 3, 4, and 5 of my tensor calculus series. The links to those videos are in the description. The main difference is that the tensor calculus videos cover polar coordinates, whereas this video will cover Rindler coordinates. The tensor calculus videos are more slow-paced than this video, so if you find this video confusing, the tensor calculus videos might help make things clearer. The first step to understanding the math of curvilinear coordinate systems is to review the multivariable chain rule. I'm only going to give some quick intuition for why this rule is true. If you want a formal proof, you'll have to search it elsewhere online. Let's start with the single variable chain rule, which tells us how to take the derivative of a nested function f of x of lambda. If we have a single variable function, f of x, and we zoom in on a small region, then the function looks like a straight line. The height of this function is df, and it's equal to a small step in the x direction, dx, times the line's slope, which is the derivative df by dx. So we have the relationship df equals df by dx times dx. Similarly, if we have a function x of lambda, when we zoom in, the function looks like a straight line, with a width of d lambda and a height of dx and a slope of dx by d lambda. We get the relationship that height dx equals dx by d lambda times d lambda. If we sub this formula in for dx in the first equation, we get that df equals df by dx times dx by d lambda times d lambda. And if we divide both sides by d lambda, we get a formula to compute df by d lambda using the product of these two derivatives. This formula is what lets us take the derivative of nested single variable functions, and is called the single variable chain rule. In the example of taking the derivative of f of lambda equals sine of lambda squared, we can set x equals lambda squared. Then dx by d lambda is just 2 times lambda, and df by dx is just cosine of x. Multiplying them and writing in terms of lambda, we get cosine of lambda squared times 2 lambda. The multivariable chain rule is similar. If we have a function of two variables, f of x and y, and we zoom in on a small region of the function, then the function looks like a flat plane. The height of this small region is again df, and it is equal to the sum of two changes. First, a small step in the x direction, dx, times the slope in the x direction, partial f by partial x. Then we add to that a small step in the y direction, dy, times the slope in the y direction, partial f by partial y. So we have df equals partial f by partial x times dx, plus partial f by partial y times dy. If we sub in single variable chain rules that relate dx and d lambda, and also dy and d lambda, and divide all terms by d lambda, we get the multivariable chain rule, which lets us take the derivative of a nested multivariable function. Let's do an example. F of lambda equals sine of lambda squared times sine of 5 lambda. We can set lambda squared equals x and 5 lambda equals y. Dx by d lambda is just 2 lambda, and dy by d lambda is just 5. Now, with partial derivatives with respect to x, we treat all other variables in the formulas as if they are constants. So we treat y as if it's a constant. So the partial derivative of sine x sine y with respect to x is cosine x sine y, and partial f by partial y is sine x cos y, since we treat x as a constant. Subbing in x and y, we get df by d lambda equals cosine of lambda squared times sine of 5 lambda times 2 lambda plus sine of lambda squared times cosine of 5 lambda times 5. Again, these are not proper proofs. I'm mostly making an appeal to intuition for why the multivariable chain rule results in a sum of terms for each variable. The idea of dividing by d lambda isn't a very mathematically rigorous or correct thing to do. If you want a proper proof of these rules, you can look them up online. So that's multivariable chain rule. Now let's look at interpreting basis vectors as tangent derivative vectors along a coordinate curve. Again, I'm going to primarily focus on intuition here instead of being formally correct. Here are some examples of curves that each have a direction associated with them. A tangent vector along a curve is basically a vector that just barely touches the curve at one point at the base of the vector. It's basically like an instantaneous velocity vector for a particle traveling along the curve. We can think of a curve as a position vector s whose tip is changing location as time goes on. We can use the path parameter lambda to indicate the vector's position at a specific point. As lambda increases, the tip of the position vector s will change location, sweeping out the shape of the path in space. So a curve is really like a vector-valued function that takes a real number lambda as input and outputs a position vector s. To get a tangent vector along this curve, we start with a position vector s of lambda, and then pick another position vector s of lambda plus h, which is a small step h ahead of the first vector. The difference of these two vectors looks like this. If we divide this difference vector by h, and then take the limit as h approaches 0, we get the derivative of s with respect to lambda, ds by d lambda. As we make h smaller and smaller, this vector becomes a vector that's tangent to the curve. So this derivative, ds by d lambda, is a tangent vector along the curve s of lambda. And actually, ds by d lambda is a whole series of tangent vectors, one tangent vector for each value of lambda along the curve. These are basically like velocity vectors along the curve, although the path parameter lambda does not necessarily have to be related to time. It can be any abstract variable without physical significance. Let's take a look at tangent vectors along a curve where the curves are the coordinate curves in a coordinate system. For example, the curves of x and ct in standard inertial coordinates for spacetime, and the curves of ct tilde and x tilde in the Rindler coordinates. We're going to find that tangent vectors along these curves actually give us the basis vectors for these coordinate systems. Let's take a look at a curve where the path parameter variable is just x. The curve is just a straight line that moves in the positive x direction. Let's say that we have a position vector s of x whose tip moves along a horizontal line according to the x variable. We also have another position vector s of x plus h, which is a small step h in front of it. To get the tangent vector along this line, let's look at the difference vector s of x plus h minus s of x divided by h for different values of h. If we set h equals 2, then the difference vector s of x plus 2 minus s of x is 2 units long. And dividing by h equals 2, this vector becomes 1 unit long. If we set h equals 1, the difference vector is 1 unit long. And dividing by h equals 1, it stays 1 unit long. If h equals 1/2, the vector is 1/2 units long, but dividing by h equals 1/2, it becomes 1 unit long again. If we take the limit as h approaches 0, then the resulting difference vector is always a horizontal vector that's 1 unit long that points in the positive x direction. This limit can be thought of as a partial derivative of the vector s with respect to the x-coordinate variable. And the result is a horizontal vector 1 unit long, which is exactly what the ex basis vector is. We can repeat this process for any point in spacetime and get the same ex vector that's 1 unit long and pointing in the positive x direction. Repeating this approach for the direction of the ct variable, we get a vertical basis vector 1 unit long, so we can think of partial s by partial ct as the et basis vector. Again, the et basis vector is the same for any point in spacetime, and it's 1 unit long pointing in the positive ct direction. We can also use this approach for the Rindler coordinates. The curves that measure x tilde are straight lines that radiate from the origin. If we apply our normal limiting approach to calculate the tangent vector partial s by partial x tilde, the tangent vectors point outward along the x tilde lines. Repeating everywhere in spacetime, we get the x tilde basis vectors, which point along the lines of constant time for accelerating observers traveling along the hyperbolas in spacetime. Unlike the ex and et basis vectors, the ex tilde basis vectors are not constant everywhere in spacetime. They change direction depending on where the base of the arrow is located. And doing the same thing for the ct tilde coordinate curves, which are the hyperbolas, the partial s by partial ct tilde vectors end up being tangent vectors to these hyperbolas. These are the et tilde basis vectors that point in the direction of constant position for accelerating observers. Note that these et tilde basis vectors not only change direction at various locations, they also change size. They get longer as we move farther from the origin. The reason for this is that a constant hyperbolic angle results in longer hyperbolic curves farther from the origin. If we travel a longer curve for the same change in the ct variable, then the tangent vector must be longer, because we are covering more distance with the same change of the variable. Since we now understand multivariable chain rule and also that basis vectors are tangent vectors along coordinate curves, let's return to the problem of changing basis in curvilinear coordinate systems. We need to figure out how to write the basis vectors et tilde and ex tilde in terms of the basis et and ex. We do this by figuring out what the coefficients in front of the basis vectors should be in these formulas. But remember, basis vectors are really just partial derivatives of the spacetime position vector s with respect to the coordinate variables. And now, filling in these coefficients is easy. We just get them from the multivariable chain rule. These first two coefficients are partial ct by partial ct tilde and partial x by partial ct tilde. And these next two coefficients are partial ct by partial x tilde and partial x by partial x tilde. So we've seen that we can write a Galilean transform of spacetime basis vectors in array notation like this, with the basis vectors written in a row and the coefficients written in a Galilean matrix. We also saw that we can write a Lorentz transformation of basis vectors in array notation using a Lorentz matrix. And now we can write the multivariable chain rule method of changing basis vectors in array notation like this, where this matrix of partial derivative coefficients is called the Jacobian matrix. We can also rewrite the basis vectors in the standard notation if we want. Let's calculate the coefficients needed to change basis between the standard spacetime coordinates ct and x and the Rindler coordinates ct tilde and x tilde. We already know the equations for ct and x from the previous videos. If we expand the time basis vector and Rindler coordinates, we see that we need to calculate these two partial derivatives with respect to ct tilde. Now, before we start taking derivatives, you might be confused about taking the derivative with respect to ct tilde. To do this, you just need to treat ct tilde as if it's a single variable. Alternatively, since c is a constant, you can also pull it out in front of the derivative as 1 over c, and just take the derivative with respect to t tilde. Both of these approaches work just fine. Also, as a reminder, the derivative of sinh is cosh, and the derivative of cosh is sinh. You can easily prove this using their exponential representations. So to get partial ct by partial ct tilde, we just take the sinh in the formula and turn it into a cosh, and then multiply the outside by the inner coefficient, alpha over c squared. We can do the same thing for partial x by partial ct tilde, except we turn cosh into sinh. We can simplify these formulas further by noticing that x tilde times cosh is just the formula for x, and x tilde times sinh is just the formula for ct. So the final coefficients to change basis are alpha over c squared x and alpha over c squared ct. We can also expand the Rindler ex tilde basis vector using the multivariable chain rule. These derivatives with respect to x tilde are just the original formulas with the x tilde variable removed. And we can also write these coefficients as ct over x tilde and x over x tilde. So we found all the coefficients in these multivariable chain rule formulas for converting between the standard spacetime basis and the Rindler spacetime basis. Writing these formulas in array notation, this also means we found the coefficients of the Jacobian matrix. We can also rewrite all these formulas using the standard basis vector notation instead of the partial derivative notation for basis vectors. We can also use this other pair of formulas derived in the last video, where ct tilde equals arctangent and x tilde equals the square root, to do the transformation of the basis vectors in the opposite direction. As a reminder, we can take the derivative of the square root of a variable q with respect to q by treating the square root as an exponent operation with a power of 1/2. We can then use power rule to bring the 1/2 in front and decrease the exponent by 1 to get negative 1/2, which gives us a half times 1 over the square root of q. And the derivative of arctangent of q is 1 divided by 1 minus q squared because the internet told me so. We can expand the standard coordinate time basis vector using chain rule. This derivative with respect to ct involves a derivative of arctangent, which gives us 1 divided by 1 minus the square of the input. We also need to use chain rule to take the derivative of the input with respect to ct, which just gives us 1 over x. If we change this 1 over x to x over x squared and multiply through, then this becomes x over x squared minus ct squared. And for the derivative of x tilde with respect to ct, we get 1/2 in front, and then put the square root in the denominator. Again, we need to use chain rule to take the derivatives of the term under the square root by ct, and this just gives us negative 2 ct. And here the 1/2 and the 2 cancel. And remember, the square root of x squared minus ct squared is just x tilde by definition. So this becomes x tilde squared, and this becomes x tilde. So our coefficients are c squared over alpha, x over x tilde squared, and negative ct over x tilde. We can follow a similar procedure to expand the standard x basis vector using multivariable chain rule. And we get the coefficients negative c squared over alpha, ct over x tilde squared, and x over x tilde. Using these coefficients, we can get the inverse Jacobian matrix. Once again, we can also rewrite these formulas using the standard basis vector notation instead of the partial derivative notation. We can try multiplying the Jacobian matrix and the inverse Jacobian matrix. This row multiplied by this column gives us first entry times first entry plus second entry times second entry. We can then fill in all the entries using this method. If we add and multiply things out, and remember that x tilde is the square root of x squared minus ct squared, we find that the result is the identity matrix. So the Jacobian and the inverse Jacobian matrices are indeed inverses. If you want, you can try and prove that the Jacobian and the inverse Jacobian always multiply to give the identity matrix in all cases, not just in the case of Rindler coordinates. The proof involves using multivariable chain rule backwards to collapse the sum of terms together. I'll leave a link to the proof of this fact in the description. It's worth noting that all the transformation matrices we've seen so far in this series, including scaling matrices, Galilean matrices, and Lorentz matrices, are all examples of Jacobian and inverse Jacobian matrices. If we look at the scaling example and rescale the coordinates x, y to be half as big to get x tilde and y tilde, then the partial derivatives end up being 1/2, 0, 0, and 1/2. These form the entries of the inverse Jacobian matrix, which is just the matrix used to transform the vector components. The Jacobian matrix is the inverse of this, a matrix of 2's along the main diagonal, and is used to transform the basis vectors to be twice as big. If we take the Galilean transform between coordinates tx and t tilde x tilde, we get 1, 0, negative e, and 1. These are the entries of the inverse Jacobian matrix, which is just the inverse Galilean matrix. with the Jacobian matrix giving the normal Galilean matrix that transforms the basis vectors. And if we take the Lorentz transformation between coordinates ctx and ct tilde x tilde, the partial derivatives are gamma, negative beta times gamma, negative beta times gamma, and gamma. These are the entries of the inverse Jacobian matrix, which is just the inverse Lorentz matrix, with the Jacobian matrix just giving us the Lorentz matrix that transforms the basis vectors. So any coordinate transformation, whether curvilinear or straight line, has its own Jacobian and inverse Jacobian matrices that can be used to transform the basis vectors and vector components. Now, the Galilean and Lorentz matrices have entries that are constant numbers and don't depend on the coordinates. But the Jacobian matrix between the standard inertial coordinates and the Rindler coordinates does depend on the spacetime coordinates. So we get a different transformation for every point in spacetime. This is exactly what we need to change to the Rindler basis, since et tilde and ex tilde basis vectors can change direction and length everywhere in spacetime. If we choose this specific point in spacetime, you can see that when we plug in x, ct, and x tilde, we get the correct basis transformation equations. Now that we have the Jacobian and the Jacobian inverse matrices, let's use them to change basis for some 4 vectors in spacetime. So recall that the 4 velocity u equals the derivative of the 4 position s with respect to proper time tau. Using multivariable chain rule, we can expand this vector in any basis that we like, where the components of the vector are the derivatives of the spacetime coordinates with respect to proper time tau. This is just like expanding a vector into its components, as we've done many times before, except this time the components come from the multivariable chain rule. We've already seen that we can use multivariable chain rule to change between the standard spacetime basis and the Rindler spacetime basis, which results in a matrix formula using the Jacobian matrix. It turns out that we can also convert between these vector components using multivariable chain rule, which results in a matrix formula using the inverse Jacobian. This makes sense. Since the basis vectors are covariant and transform with the Jacobian matrix, vector components are contravariant and transform in the opposite way with the inverse Jacobian matrix. The opposite changes cancel out, and we can write the same invariant vector using a different basis with different components. Now that we understand how the Jacobian and inverse Jacobian can help us change basis and change the components of a 4-velocity vector, let's look at an example. Let's say that Einstein is standing still in our spacetime diagram with a vertical world line, and Rindler is accelerating to the right with constant proper acceleration alpha along a hyperbolic world line. You should know by now that Einstein will have a 4-velocity vector u at every point along his world line. The 4-velocity vectors are invariant and are agreed upon by all observers. But the vector components that Einstein measures in the basis ET-EX will be different than the components Rindler measures in the basis ET-EX. Given what we've learned in this video, let's get the components of these 4-velocity vectors using multivariable chain rule, and then use our knowledge of the Jacobian and inverse Jacobian matrices to change from Einstein's components to Rindler's components for these 4-velocity vectors. Doing this in Einstein's frame will involve calculating the derivatives dct by d tau and dx by d tau. This means that we need equations for Einstein's world line using Einstein's proper time tau as the path parameter. Let's say that Einstein is stationary with a constant position of c squared over alpha, where c squared over alpha is also referred to as the Rindler distance, denoted with a capital D. The ct coordinate in this case is simply the proper time according to Einstein, c times tau. Obviously, the x-coordinate is constant, so dx by d tau is 0, and dct by d tau is c. When we expand the 4-velocity ds by d tau using multivariable chain rule in Einstein's basis, we can plug in the components dct by d tau and dx by d tau, and we see that the 4-velocity is just c times the time basis vector, with 0 space components. This is the expected result for a stationary observer that has 0 velocity in space. But now we want to get Einstein's 4-velocity vector components according to Rindler, using the et tilde and ex tilde basis vectors in his coordinate system. Or equivalently, the tangent vectors partial s by partial ct tilde and partial s by partial x tilde. We know that we can convert between Einstein's components and Rindler's components using multivariable chain rule, whose equations are summarized by this matrix multiplication with the inverse Jacobian matrix. We can then use the inverse Jacobian that we calculated earlier and plug in Einstein's 4-velocity components of c and 0. After doing the matrix multiplication, these terms go to 0. So we already know the components of u in Einstein's frame, but if we sub these in, we get the components of u in Rindler's frame. We get c times c squared over alpha times x over x tilde squared for Rindler's time component, and negative c times ct over x tilde for Rindler's x component. If we recall that the x-coordinate for Einstein's path is a constant value of x equals c squared over alpha, we can sub this in for x. And since c squared over alpha is just the Rindler distance d, we can replace this pair of c squared over alpha terms with d squared. So we have Einstein's four-velocity vector components written in Rindler's basis, and we can confirm that they make sense based on our spacetime diagram drawing. When ct equals 0, Einstein is on the x tilde axis, at a position of x tilde equals d. This means that at ct equals 0, Einstein's four-velocity vector points completely along the et tilde direction, which is completely vertical and matches our spacetime diagram. For ct greater than 0, the time component is positive and the x component is negative, which matches our picture. And for ct less than 0, both the time and the x components are positive, which also matches our picture. We can also look at the example of Rindler's four-velocity vectors and try to get the components in Einstein's basis. We'll say that Rindler maintains a constant proper distance, x tilde equals c squared over alpha from the origin, which is his Rindler horizon, and that his time coordinate ct tilde is just c times the proper time in his own frame. The derivatives with respect to tau are just c and 0, so his four-velocity vector has components c and 0 in his own frame. If we want the components of Rindler's four-velocity vector according to Einstein's frame, we can convert between the components using multivariable chain rule, which results in a matrix formula that uses the Jacobian matrix. If we get the Jacobian matrix we calculated before and multiply by Rindler's four-velocity components in his own frame, then these terms go to 0. And Rindler's four-velocity components in Einstein's frame are just c times alpha over c squared times x for the time component, and c times alpha over c squared times ct for the x component. And again, if we recall that c squared over alpha is the Rindler distance, we can replace alpha over c squared with 1 over d. We now have Rindler's four-velocity vector components written in Einstein's basis, and we can again confirm that they match our diagram. On the x-axis, where ct equals 0 and x equals d, Rindler's four-velocity is completely vertical, as expected. And for ct greater than 0, its time and x components are both positive, so it points toward the upper right. And for ct less than 0, the time component is positive, but the x component is negative, so it points to the upper left, also as expected. So to summarize this video, we learned the multivariable chain rule, and we learned that basis vectors can be thought of as tangent vectors along coordinate curves, which is the derivative of a position vector with respect to a coordinate variable. Using the multivariable chain rule, we can expand the four-velocity vector into any basis that we like, where the four vector components are the derivatives of coordinates with respect to tau. We can also use the multivariable chain rule to convert between basis vectors, written in matrix form using the Jacobian matrix, and convert between the vector components, written in matrix form using the inverse Jacobian matrix. One very last thing I'll point out is that the four-position vector S is normally written CTET plus XEX in Einstein's frame. But in Rindler's frame, S is written as just x tilde times EX tilde, with no time component at all. This is because the EX tilde basis vector always points in a direction parallel to S, so S's time component is always 0 in Rindler's basis. We'll talk about this more in the next couple videos. In this video, we're going to talk about the twin paradox and how to calculate the proper time along curved world lines using the Minkowski and Rindler metric tensor matrices. Let's start with the twin paradox. The twin paradox involves two observers, Alice, who stays home on Earth, and Bob, who goes on a round-trip journey on a rocket close to the speed of light. Some people will argue that, since special relativity tells us that moving clocks run slow, Alice will see Bob's clock tick more slowly than her own clock. This means that when Bob arrives back home on Earth and compares his clock with Alice, Bob's clock will have counted less time than Alice's clock. The argument continues that in special relativity, since everything is relative, all frames of reference are equally valid. Therefore, we can also view this situation as Bob's rocket being stationary, and Alice and the Earth going on a round trip relative to Bob. In this case, Alice's moving clock ticks more slowly than Bob's clock, and when they compare clocks, Alice's clock will have counted less time than Bob's clock. The argument goes that this is a contradiction that disproves special relativity. This argument turns out to be wrong, and the key mistake is assuming all reference frames are equivalent. Special relativity does not say this. It only says that all inertial frames are equivalent. And in the twin paradox scenario, at least one of the two frames must be non-inertial, and so the frames are not equivalent to each other. To understand why the twin paradox is incorrect, we need to understand how to calculate proper time. In Relativity 104 Part E, we learned about the proper time tau, which is the time measured on a clock that's traveling with the observer. We started with the four-position spacetime vector S, which indicates a position in spacetime. Then we defined the Minkowski metric, which says that for inertial frames, the dot product of the time basis vector with itself is +1, and the dot products of a space basis vector with itself is -1, and the mixed basis dot products are 0. From there, we defined the spacetime interval S squared, which is S dot S, which in inertial frames is ct squared minus x squared minus y squared minus z squared. We said that a vector was time-like when S squared was greater than 0, and for time-like vectors, S is the speed of light c times the proper time tau. This is also called the vector's Minkowski length because it is calculated with the Minkowski metric. In this video, you will hear me call tau the proper time, but sometimes I will also call c times tau the proper time. Tau is the proper time measured in time units, like seconds, and c times tau is the proper time measured using space units, like meters. To measure a time in meters, we just measure how long it takes for a beam of light to travel that number of meters. So if we assume the y and z coordinates are 0, the four-position vector only has time and x components. If we want to know how much proper time goes by on this world line between these two event points, we just get the components of the four-position vector using our spacetime basis. To build this four-position vector, we need 5 time basis vectors and 3 x basis vectors. And plugging the components 5 and 3 into our formula for proper time, we get that c times tau is equal to 4. Now, let's say that we have an observer that travels to the right, then stands still, then travels left, and then stands still again. The world line for this observer is not a straight line. So how do we figure out how much proper time has passed on a clock that's traveling on this world line? We can find the total proper time just by adding up the proper times for each individual linear segment of the world line. The first segment is given by the vector S1, which is 4 time units and 3 space units to the right. The second segment, S2, is 2 time units and 0 space units. The third segment, S3, is 2 time units and 1 space unit to the left. And the last segment, S4, is 1 time unit and 0 space units. For S1, the time component is 4, and the x component is 3. So the proper time c times tau equals the square root of 4 squared minus 3 squared. This is the square root of 16 minus 9, or just the square root of 7. For S2, we can read c times tau equals 2 directly from the time component of the vector, since the vector has 0 space components and therefore no time dilation happens to the proper time. For S3, the components are 2 and -1, so c times tau ends up being just the square root of 3. And again, for S4, we can read c times tau equals 1 directly from the time component, since the space components are 0. If we add up all these proper times together, we get the square root of 7 plus 2 plus the square root of 3 plus 1, which ends up being about 7.38. So we've calculated the total proper time along this non-straight world line just by adding up the individual proper times for each segment. We can also apply this technique for our twins in the twin paradox scenario. Alice stays home on Earth, and so she has a straight vertical world line, which we can represent by the vector SA, which is 6 time units long and 0 space units long. Bob does a there and back journey on his rocket ship, so his world line through spacetime is a combination of 2 linear segments, given by the vectors SB1 and SB2. SB1 equals 3 time units and positive 2 space units, moving to the right, and SB2 equals 3 time units and negative 2 space units, moving to the left. Using our formula for proper time, it's not hard to see that Alice's proper time is just 6. C times tau is just 6. And if we calculate the proper time for the 2 segments of Bob's world line, we get the square root of 5 plus the square root of 5, which is about 4.47. So given these results, we find that Alice's total proper time of 6 is actually greater than Bob's total proper time of 4.47. So even though Alice and Bob start and end their journeys at the same points in spacetime, Bob actually experiences less proper time overall than Alice. So this is a very important concept to understand in special relativity. Proper time doesn't just depend on the start point and end points of a world line. The proper time also depends on the path you take through spacetime. In some ways, this is similar to physical space. In New York City, on the island of Manhattan, most roads are arranged on a grid, but there's one street called St. Nicholas Avenue that runs diagonally through the grid. It should be common sense to us that traveling along the streets in the main grid, along vector b1 and then along vector b2, will give us a different distance than traveling diagonally along the vector a, which is the vector sum of b1 and b2. The total length of the vectors b1 and b2 is actually longer than the length of the vector a. Mathematically, this is stated as the length of b1 plus the length of b2 is greater than or equal to the length of a, where a is just the vector sum of b1 and b2. This is called the triangle inequality. It basically means that the lengths of any 2 sides of a triangle added together will always be longer than the third side. We have a similar situation in spacetime, with Alice's straight world line and Bob's zigzag world line. Traveling along Bob's world line, along vectors SB1 and then SB2, will give us a different proper time than traveling along Alice's world line, SA, which is just the vector addition of SB1 and SB2. Except now, there's a key difference. Traveling along SB1 then SB2 actually gives us a shorter proper time than traveling along SA. So the Minkowski length of SB1 plus the Minkowski length of SB2 is actually less than or equal to the Minkowski length of SA, which is the vector sum of SB1 and SB2. This is the reversed triangle inequality, where the inequality sign is the opposite of the sign we saw for the triangle inequality in physical space. This inequality only applies for time-like vectors, which are vectors that are more vertical than the world lines of light beams in a spacetime diagram. So in physical space, the triangle inequality tells us that when we have 2 vectors, b1 and b2, and add them together to give a third vector, a equals b1 plus b2, then the sums of the lengths of b1 and b2 will always be equal to or greater than the length of a equals b1 plus b2. This basically means that a straight line is always the shortest distance between 2 points. Any zigzagging we do will make the path longer. But in spacetime, it's the opposite. The sum of the Minkowski length of time-like 4 vectors, SB1 and SB2, will always be smaller than the Minkowski length of the sum of the vectors. This basically means that, in an inertial frame, a straight line between 2 points will have the longest possible proper time between those 2 points, and that doing a zigzag will actually decrease the proper time between the points. So coming back to our twin paradox, the fact that Bob experiences less proper time than Alice makes sense if we accept the idea that a straight line between points in spacetime will always have the longest possible proper time in inertial frames, and that doing a zigzag path will actually decrease the proper time. Now, in the twin paradox, some people will claim that the situation of Alice standing stationary on Earth and Bob doing a there and back journey is completely equivalent to a reference frame where Bob is stationary and Alice is moving on a there and back journey, meaning Bob now has the straight line path that takes the longer time. And supposedly this contradiction proves that special relativity is inconsistent. But this line of reasoning is not correct. If we assume Alice's world line is inertial, then Bob's world line is non-inertial, because he will experience a fictitious force when he changes direction. This makes Bob's world line fundamentally different than Alice's inertial world line. Recall that the first postulate of special relativity says that the laws of physics are the same in all inertial reference frames. This basically means that all inertial frames are equivalent to one another. And remember, we use Lorentz transformations to switch from one inertial frame to another. Anytime we have an inertial spacetime basis, which is a Minkowski orthonormal basis, we can always change to another inertial spacetime basis using a Lorentz transformation. So if Alice has a straight world line that's stationary in space, and Bob also has a straight inertial world line that's moving to the right, it's possible to use a Lorentz transformation to make Bob's world line look stationary like Alice's, where Alice looks like she's moving to the left. A Lorentz transformation can change straight lines into straight lines on a spacetime diagram. But if Bob has a there and back zigzag-shaped world line, it's impossible to use a Lorentz transformation to change it into a straight inertial line, like Alice's. A Lorentz transformation cannot change a zigzag into a straight line. So the resolution of the twin paradox is that if Alice's frame is inertial, then Bob's frame must be not inertial, and these are fundamentally different in special relativity because we cannot make Bob's world line look like Alice's using a Lorentz transformation. It's perfectly fine that Bob's clock measures less time than Alice's. Now that we've resolved the twin paradox, the next thing I'll do in this video is show how to calculate the proper time along a curved world line in a given coordinate system. The key to calculating proper time is the metric tensor, specifically the Minkowski metric in inertial coordinates and the Rindler metric in Rindler coordinates. In my tensor calculus videos 11 and 12, I show how to get the physical length of a curve in physical space by approximating the curve as a series of straight lines and adding up the lengths of these lines. Let's say that a curve is given by a position vector r that moves around in space based on a parameter lambda. To get the length of a line segment, we take the position vector at the start, r of lambda, and the position vector at the end, r of lambda plus delta lambda, then subtract the vectors, and then calculate the length of the resulting vector, and then sum up the lengths of each segment vector to approximate the curve's length. Here, delta lambda represents the spacing between the endpoints of the line segments. If we multiply and divide the lengths by delta lambda and take the limit as the spacing between the endpoints gets smaller and smaller, our sum becomes an integral, and this difference vector over delta lambda becomes the tangent vector dr by d lambda. So the key to calculating the physical lengths of curves is knowing the lengths of the curve's tangent vectors, which we can calculate using the metric. To see this explained in greater detail, check the description for links to the tensor calculus videos 11 and 12. It turns out that in spacetime, we can also calculate the total proper time along a curved world line by approximating the curve as a series of straight world lines. We take spacetime position vectors for all the world line endpoints, subtract them in pairs to get the difference vectors, and then sum up the Minkowski lengths of all the world line segments to approximate the total proper time on the world line. To get the exact proper time value, we take the limit as the spacing of the endpoints goes to 0. We get an integral of the Minkowski length of the tangent vector ds by d lambda times d lambda. Also, I just want to point out that the world line's tangent vector ds by d lambda is not the same thing as the world line's four-velocity vector ds by d tau. The four-velocity vector ds by d tau always has a Minkowski length of c, but a generic tangent vector ds by d lambda can have any Minkowski length. The two vectors are related by the single variable chain rule using d tau by d lambda. So the key to calculating proper time along curves is getting the Minkowski length of the tangent vector ds by d lambda. And the length of the tangent vector is given by the square root of the dot product of the tangent vector with itself, which we can calculate using the metric tensor for whichever coordinate system we're using. In Relativity 105b, I introduced Rindler coordinates, ct tilde and x tilde, which are a non-inertial coordinate system for an accelerating observer, with proper acceleration alpha. This observer travels on a hyperbola with a constant Minkowski distance of d equals c squared over alpha from the origin. In this part of the video, we're going to calculate the proper time along a hyperbola located at a constant proper distance of 4d from the origin. We're going to do this both in the standard inertial coordinates using the Minkowski metric and also the Rindler coordinates using the Rindler metric, and we're going to find that our result of the proper time along the curve ends up being the same in both cases. To do our calculations, I'm just going to remind you of this fundamental hyperbolic trig identity, cosh squared minus sinh squared equals 1, because we're going to be using it a lot. Also, remember that the derivative of cosh is sinh, and the derivative of sinh is cosh, which we can show easily using the exponential representations. So in the standard inertial coordinates, this hyperbolic world line is described by parametric equations. The time variable ct is equal to 4d times sinh of lambda, where again, lambda is our path parameter. And the position variable x is given by 4d times cosh of lambda. This lambda variable increases as we travel along the hyperbola, and again, lambda does not have any direct physical meaning. Remember, our goal is to calculate the tangent vector ds by d lambda. We can expand this tangent vector using multivariable chain rule, and see that the components of this vector are dct by d lambda and dx by d lambda. dct by d lambda is 4d times cosh of lambda, and dx by d lambda is 4d times sinh of lambda. Plugging these in, we have a vector formula for the tangent vector ds by d lambda. When lambda is equal to 0 on the horizontal axis, sinh of 0 equals 0, and so this tangent vector is completely vertical in the time direction. If we plug in different values of lambda, we see that this tangent vector is in fact always tangent to our world line, as expected. If we plug this into ds by d lambda dotted with itself and expand, we get 4 terms. If we recall the Minkowski metric for spacetime basis vectors, et equals +1, ex.ex equals -1, and the cross terms go to 0. And using the fundamental hyperbolic trig identity, this simplifies to 4d all squared. If we plug in the length of the tangent vector into our proper time integral, the square root term is constant, and we can just pull it outside of the integral. And the
I'll be right back.
antiderivative of d lambda is just lambda. So this becomes the final value of lambda minus the initial value of lambda. So now we have a formula for the proper time along this curved world line. This formula is basically a translation between our path parameter lambda and our proper time tau, or equivalently c times tau. It tells us how much proper time has passed on the curve between known values of lambda. For example, if the final value of lambda is positive 2 and the initial value of lambda is negative 1, plugging this into our formula, we get the total proper time c times tau along a segment of the curve is equal to 12d. Now, let's redo this same calculation of getting the proper time along this curved world line, but this time let's calculate the result in the Rindler coordinates. First, we need to convert the standard inertial coordinates ct and x into Rindler coordinates ct tilde and x tilde. We already derived the formulas for this conversion in Relativity 105 Part B. X tilde is just the positive square root of x squared minus ct squared. Plugging in these formulas and factoring out 4d and setting this to 1 by the fundamental hyperbolic trig identity, we get that x tilde is a constant value of 4d along this curve. We also know that ct tilde equals d times arctanch of ct over x. Plugging in ct and x, the 4d's cancel, and sinh over cosh becomes tanch. Since arctanch and tanch are inverse functions, they cancel out and we just get the input argument lambda. So ct tilde equals d times lambda. So the parametric equations for this world line are a lot simpler in Rindler coordinates. Again, we need the tangent vector ds by d lambda, which equals this multivariable chain rule expansion. dct by d lambda is just d, and since x tilde is a constant, its derivative with respect to lambda is 0. Plugging these in, we get that the tangent vector is just d times et tilde, with no x component. Since et tilde is always tangent to this hyperbolic curve, it makes sense that the tangent vector ds by d lambda is just a scalar multiple of et tilde. Now, ds by d lambda dotted with itself is just d squared times et tilde dot et tilde. Now, a problem here is that we've never calculated the dot products of the Rindler basis vectors before. In other words, we don't know the Rindler metric yet. But it's not difficult to figure out. From Relativity 105c, we learned the multivariable chain rule formulas for changing from the inertial basis to the Rindler basis. So we can take et tilde dot et tilde and expand it in terms of the et and ex basis vectors. After we distribute, the et dot ex terms go to 0. And remember, et dot et equals positive 1 and ex dot ex equals negative 1. And also remember that cosh squared minus sinh squared equals 1. So we get that et tilde dot et tilde equals x tilde over d all squared, which is also x tilde times alpha over c squared all squared. It's not hard to show that et tilde dot ex tilde is 0, and ex tilde dot ex tilde is negative 1. Now that we have the Rindler metric, which lets us calculate the lengths of vectors in the Rindler basis, let's go back to calculating the length of ds by d lambda in Rindler coordinates. This dot product of basis vectors is x tilde over d squared. These d squareds cancel and we just get x tilde squared. But remember, on our world line in this example, x tilde is just equal to the constant value of 4d. So the dot product of the tangent vector with itself is 4d all squared, which is exactly what we got last time in the standard inertial coordinates. This means that our formula for the proper time along our world line is the exact same as before. C times tau equals 4d times the final value of lambda minus the initial value of lambda. Again, if the final value of lambda is plus 2 and the initial value of lambda is negative 1, plugging this into our formula, we get that the total proper time, c times tau, along this segment of the curve is 12d. So we've shown that the proper time along a curve is the same whether we measure it in an inertial coordinate system or the non-inertial Rindler coordinate system. But this fact is not surprising, because the proper time along curves is just a result of this arc length integral with this tangent vector. And the tangent vector is an invariant 4 vector, which doesn't depend on any coordinates at all. We can expand the tangent vector in terms of different bases using multivariable chain rule and get different components for it, but the tangent vector itself is invariant and unchanging. And that means that the Minkowski length of the tangent vector, which is the square root of the vector's dot product with itself, is also an invariant quantity. And here's one last fact. When integrating over the path parameter lambda, we got a relationship between lambda and the proper time along the path. But as I said before, the path parameter we choose for the integral doesn't matter. If I change the path parameter to the Rindler time ct tilde, it's possible to get a relationship between the proper time c times tau and the Rindler time ct tilde along Rindler hyperbolas with constant x tilde. If we compute this integral, remembering the Rindler metric and that the x tilde coordinate is constant, then we get that the proper time along a curve of constant x tilde is x tilde over d times the final time minus the initial time. If we assume that the starting time is 0, we just get x tilde over d times ct tilde. This formally proves what we assumed in Relativity 105 Part B. The proper time c times tau along a hyperbola in Rindler coordinates is not equal to the coordinate time ct tilde. They are only the same in the special case of x tilde equals d. Otherwise, the clocks with larger x tilde values will tick more quickly, because they get more proper time for a single unit of t tilde. The reason for the faster ticking clocks, to the right, is because the et tilde basis vector gets longer and longer for large x tilde. So the et tilde dot et tilde component of the Rindler metric grows to the right. This tells us that when the time basis vector is longer, it indicates a clock that ticks more quickly along a coordinate curve of constant position in that coordinate system. To summarize this video, I explained that the twin paradox is not a true paradox because if Alice's world line is inertial, then Bob's world line is non-inertial, and so the world lines are not equivalent. Alice's world line experiences longer proper time because a straight inertial world line always has the longest proper time between any two event points, by the reversed triangle inequality. We also showed how we can integrate a tangent vector along curved world lines to get the total proper time along that world line. And the result is the same in all coordinate systems because the tangent vectors are invariant and don't depend on the coordinate system. I also want to clear up a possible point of confusion before this video ends. In this video, I said that a straight inertial line between two event points will always have the longest possible proper time. But in previous videos, I said that the proper time is the shortest possible time between two events. Some people might be confused how these are both true at the same time. When I said the proper time is the shortest possible time between 2 points, I was talking about a clock moving in spacetime along a single vector, and what happens when we measure the components of this vector in different reference frames. The time where the two events happen at the same position, the proper time, will always be the shortest of all of these times. All the other reference frames will see this time increased due to time dilation, because they see the clock moving in their frame. And in this video, when I said that a straight inertial world line between two events will always have the longest possible proper time, I was referring to looking at all possible world lines that join these two events. Each world line will have its own clock and its own proper time. The straight inertial world line will have the longest proper time of all of these world lines, because of the reversed triangle inequality for time-like vectors in spacetime. The other world lines will have shorter and shorter proper times the more bent the world line is, approaching a proper time of 0 as we approach the speed of light. In this video, we're going to talk about the covariant derivative in flat spacetime. I've already done 5 videos on the covariant derivative in my tensor calculus series, which covers the covariant derivative in flat space, curved space, and abstract Riemannian manifolds. So you can check the description for links to those videos if you want. In this video, I'm only going to talk about the covariant derivative specifically for the case of flat spacetime. Covariant derivatives in curved spacetime will come in a later video. In my Relativity 104F video, I did a number of examples of taking derivatives of spacetime 4 vectors. For example, I took the derivative of 4 velocity u with respect to proper time tau to get the 4 acceleration a. However, when I took these derivatives, I was working in an inertial reference frame, where the basis vectors are constant everywhere in spacetime. This made things simple because when I took the derivative of a term that was a vector component multiplied by a basis vector using product rule, I could ignore the part of the result that had a derivative of the basis vector. Since basis vectors are constant everywhere in inertial frames, the derivative went to 0 and I didn't have to worry about it. So inertial frames are nice because the basis vectors are constant, and their derivatives always go to 0. However, in non-inertial frames of reference, the basis vectors are changing everywhere in spacetime. In the past couple videos, we've seen that in Rindler coordinates, basis vectors can change size and direction at different points in spacetime. This means that if we need to take the derivative of a 4 vector in Rindler coordinates or other non-inertial coordinate systems, the derivatives of the basis vectors could be non-zero, so we can't ignore basis vector derivatives. To take the derivative of a 4 vector properly, we need to use product rule to differentiate both the vector components and the basis vectors. The basis vectors might change in non-inertial frames, so we need to be sure to include their derivatives. As I've said many times before, basis vectors and vector components are like two sides of the same coin. We can't talk about one without also talking about the other. A derivative that makes physical sense needs to take the change of both vector components as well as basis vectors into account in order for it to make sense. In flat spacetime, the covariant derivative just means taking a derivative where we remember to take the derivatives of basis vectors into account. It basically just means we take the derivative properly and don't ignore changing basis vectors. The definition of covariant derivative gets a little more complicated in curved spacetime. But for now, when I say take the covariant derivative of a 4 vector, we just mean that we differentiate both the vector components and the basis vectors. We're going to do 3 examples of covariant derivatives in this video. First, in Rindler coordinates, we'll take the derivative of 4 position s with respect to proper time to get the 4 velocity u. Then again in Rindler coordinates, we'll take the derivative of 4 velocity u with respect to proper time to get the 4 acceleration a. And finally, we'll take the derivative of a generic 4 vector v with respect to a generic path parameter lambda, and we'll do it in a way that works in any coordinate system, not just the Rindler coordinates. Also, in this video, when I write variables or basis vectors without any markings on top, they represent inertial coordinates, which show how an inertial observer measures time and space. Variables and basis vectors with a tilde on top represent Rindler coordinates, which show how a non-inertial observer with constant proper acceleration measures time and space. And variables and basis vectors with a smile on top represent a general coordinate system, which can be any set of arbitrary curves that form a grid pattern on the spacetime diagram. Before we do any covariant derivatives, let's do a quick review of Rindler coordinates. First, I'm going to remind you that in Relativity 105b, we learned the equations for converting between inertial coordinates and Rindler coordinates, which are the spacetime coordinate system for an observer traveling with constant proper acceleration alpha. Then in Relativity 105c, we learned about the multivariable chain rule, and also that basis vectors are actually tangent vectors along coordinate curves. These two facts allowed us to find basis change equations from inertial coordinates to Rindler coordinates, summarized in this matrix equation with the Jacobian matrix. And we can rewrite all these equations with the standard basis vector notation instead of the tangent vector notation. And we also learned how to do this in the reverse direction with the inverse Jacobian matrix. Now, in inertial coordinates, the four-position vector S equals ct et plus xex. But using the change of basis equations I just talked about, we find that in Rindler coordinates, S just equals x tilde ex tilde, with 0 time component. This is because the four-position vector S is always parallel to the ex tilde basis vector in Rindler coordinates. So we can build S completely out of ex tilde basis vectors. And technically speaking, a 4-vector should have 4 components in spacetime, but I'm going to assume that the y and z components are 0 in this video for simplicity, and just use time and x. With the review out of the way, let's take the covariant derivative of the four-position vector S with respect to proper time tau. So basically, we have an observer whose four-position vector S is moving along a world line parameterized by the proper time tau. And we want to find the four velocity vectors u for the observer on this world line. The derivative of S in inertial coordinates is easy, because we only need to take the derivatives of the vector components. The basis vectors are constant everywhere in spacetime, and we can ignore them when we take derivatives. But in Rindler coordinates, the basis vectors can change from point to point. So to take this derivative, we use product rule to get one term with the derivative of the vector component and another term with the derivative of the basis vector ex tilde. The derivative of the ex tilde basis vector is the hard part of this equation. To make it a bit easier, we can use multivariable chain rule to break this derivative down into 2 parts. Our new job is to figure out the derivative of the ex tilde basis vector in the direction of the ct tilde coordinate and the direction of the x tilde coordinate. Remember, using multivariable chain rule, we already found the equations of the Rindler basis vectors in terms of the inertial basis vectors. We can take the derivative of ex tilde in the x tilde direction by subbing in this formula for ex tilde. It turns out that there's nothing in this formula that depends on x tilde. Ct tilde does not depend on x tilde by definition, since it's an independent coordinate, and et and ex are inertial basis vectors that are constant everywhere in spacetime, so they don't depend on ex tilde either. So this derivative is just the 0 vector, meaning ex tilde does not change in the x tilde direction. We can also calculate the derivative of ex tilde in the ct tilde direction. Once again, et and ex are constant, so we just differentiate this formula with respect to ct tilde. Sinh becomes cosh, and cosh becomes sinh, and we multiply both of these terms by their inner constants, because of chain rule. Now, this big formula looks exactly like the formula for the et tilde basis vector if we were to divide it by x tilde. So this derivative is just equal to et tilde divided by x tilde, or in other words, multiplied by 1 over x tilde. So returning to the derivative of ex tilde with respect to tau, expanded using chain rule, we've found this derivative in the x tilde direction is 0, and this derivative in the ct tilde direction is 1 over x tilde times et tilde. So when taking the covariant derivative and doing product rule, we now know the value of this basis vector derivative. And canceling these x tilde terms, we get the final result for the covariant derivative of S with respect to tau in Rindler coordinates. And this result is not very surprising. It's the exact same formula we would get if we were to expand ds by d tau using multivariable chain rule in Rindler coordinates. We just calculated this same result in a slightly different way. So part of this result comes from the derivative of S's component, and the other part of the result comes from the derivative of S's basis vector. And we need both parts or else we get the wrong answer. As a sanity check to make sure this formula makes sense, we can test it out on our hyperbolic world line, which is a world line with constant proper acceleration alpha. For this world line, ct tilde equals c tau, and x tilde equals the constant value of c squared over alpha. We get the expected result of an observer who has no x velocity, so they believe they are stationary. And the time component of their forward velocity is c, which is what stationary observers should have. However, this general formula for the forward velocity will work for any world line that we can come up with that is parameterized in Rindler coordinates, not just this hyperbolic world line here. For this second part of the video, let's take the covariant derivative of the forward velocity u to get the forward acceleration a in Rindler coordinates. So just to be clear, the components of u in any coordinate system are always equal to the derivatives of the coordinate variables with respect to tau. We know this because u is equal to ds by d tau, and expanding its components using multivariable chain rule, the components are just the derivatives of the coordinate variables with respect to tau. Now, of course, taking the derivative of u in an inertial frame is easy, because we can ignore the derivatives of the constant basis vectors, and we just take the derivatives of the components. So we get the second derivatives of the coordinate variables with respect to proper time. But in Rindler coordinates, this derivative is harder. To take the derivative of both of these terms, we need to use product rule twice, to get one set of terms with the derivatives of the components, and another set of terms to get the derivatives of the basis vectors. Fortunately for us, we already calculated the derivative of ex tilde in the previous part of the video. But now we need to calculate the derivative of et tilde with respect to tau. We can use the same strategy as before, expanding the derivative using multivariable chain rule, and computing the derivatives of the basis vector in the ct tilde and x tilde directions. So looking at the derivative of et tilde in the x tilde direction, we can treat ct tilde as constant since it is an independent variable, and we can treat et and ex as constant since they are inertial basis vectors. This means that we just differentiate with respect to x tilde, which means the x tildes in this formula go to 1. And the result we get is just the et tilde basis vector divided by x tilde. As for the derivative of et tilde in the ct tilde direction, we treat x tilde, et, and ex as constant and differentiate with respect to ct tilde. So cosh becomes sinh becomes cosh, and we multiply by the inner constant by chain rule. And all of this is just the ex tilde basis vector, but with all the terms multiplied by these repeated constants and x tilde. So this derivative equals the square of alpha over c squared times x tilde times ex tilde. If we use the definition of the Rindler distance, capital D, we could also rewrite this as x tilde over d squared times ex tilde. So given the chain rule expansion of d et tilde by d tau, if we sub in the basis vector derivatives that we calculated in the direction of the coordinate variables, we get the full expression for this derivative here. So going back to our original covariant derivative of u with respect to tau, we already had the ex tilde derivative from before. And just now we calculated the et tilde derivative, so we can sub these in. Also, if we replace ut tilde with dct tilde by d tau, and replace ux tilde with dx tilde by d tau, and distribute, we get this. So this is our final result for the covariant derivative of forward velocity with respect to tau in Rindler coordinates. As you can see, the formula is pretty complicated. We get the ordinary second derivatives of the components that we expect, but we also get extra terms because of the derivatives of the basis vectors. Again, we can do a sanity check and test this formula on our standard hyperbolic world line, where ct tilde equals c tau and x tilde equals the constant c squared over alpha. We get the expected result of a constant proper acceleration alpha in the positive ex tilde direction. But again, this general formula for the forward acceleration works for any world line that we can invent, as long as it is parameterized in the Rindler coordinates. For the last part,
I think I'm gonna take a break now. I'm gonna go eat something and then meditate for a little bit. Then I think I'm gonna come back and start studying. Start learning the Manning library. So see you soon.